Okay, so the plan today is I'll just take a few minutes to tie some loose ends on some of the points that I wanted to emphasize on Simplex, and then hand over charge to Madhukar, who will discuss recurrence neural network verification, a technique for doing that. Okay, so just to recollect your memory, so the way Simplex works is it after the pre-processing, where it introduces a new variable, which is called the additional or auxiliary variable for every term that occurs in your original formula. And then and there are equalities to equate those variables to the terms that they denote. And all the constraints are expressed on these additional variables, the inequality constraints. And then it partitions all the variables, the union of the additional variables and the original, the program variables like X and Y, into two sets called basic and non-basic variable. Okay, so the basic variables to begin with are exactly all the additional variables that are introduced, and the non-basic variables are the program variables X and Y. That is to begin with. And it goes through as it goes through a sequence of pivot and update operations. That's what the algorithm does repeatedly. Variables can move between the non-basic. So the non-basic variables are associated with the rows in this tableau, X and Y, and the basic variables are associated with the rows. Okay, the non-basic variables, by the way, are also sometimes referred to as slack variables, because the slack variables, the ones in the column, are always satisfy their constraints. Okay, their lower and upper bound constraints. If there are any variables that do not satisfy their lower and upper bound, they would be among the basic variables in the that are associated with the rows. Okay, so to start with, they're called slack variables because they do satisfy their constraints, and therefore, which means that they are within their bounds, and so there is potentially some slack in their values that could be used to adjust. So, in order to make those variables among the basic variables that are violating their constraints to meet their lower and upper bound. And that's what the pivot and update operation does. Okay, so each time it picks. Okay, yeah. In addition to that, the algorithm, of course, maintains, as I mentioned, a variable ordering. And ordering is strict ordering on all the variables to decide which ones to fix and which ones to adjust. Okay, so and it is done. Yeah, it is the lowest variable in that ordering that is picked when you have a choice among the various variables to fix and the slack variables to pick to adjust. Okay, so that is the background. Okay, therefore, and so for example, here to begin with, you start with all variables initialized to 0, which corresponds to A, and then you decide to. In this case, we picked S1 because S1 was, certainly not satisfying the assignment. S2, in this case, S1 and S3 were the two variables in the basic set that were violating the constraints. We choose S1 because that's the smallest in the variable ordering that among the variables that violate. And we use X2 because that's the smallest variable to adjust to make to fix the value of S1 to put it to make it satisfy its constraint. Okay, and that's what is done. So the pivot and update operation first chooses the variables, the basic variable and the slack variable. And figures out how much the slack variable has to be either increased or decreased to make S1 the basic variable to meet its constraint. So that's what is indicated here. S1X. S1 is the basic variable that we choose to fix, and X is the variable that is adjusted, the slack variable that is adjusted. After we do such a this pivot and the update operation as per this, which is what the algorithm switches these two variables. Okay, so it moves S1 to non-basic. That makes it the slack variable, because now that has been fixed to get its value within the bounds. And X, as a result of adjustment, can potentially violate its constraint, and therefore it is moved to the basic set. And then you adjust the equations so that always you have to express the non-basic variable in terms of the slack variables, and that's what is done from here. And this operation is repeated. So the important thing is that the algorithm adjusts or fixes one variable among the basic variable, one at a time. Okay, until all the variables in the basic set meet their respective lower and upper bound. And since the slack variables always preserve the operations done such that these slack variables always maintain their constraints. So when all the basic variables are fixed to satisfy their constraints, you can be sure that all the variables satisfy constraints, and therefore you have a satisfying assignment. Okay, so that is the idea. So in this case, first we choose to fix S1 using X, then so that leaves still S3. That fixes S1, and S2 is already fixed, and so S3 is the only remaining one, and that also happens to be the smallest in the variable ordering. And Y is picked this time because X, that's the smallest among the slack variables. So at this point, yeah, and that's why it is then that is fixed, and that moves from A, B to C, which is within which is a satisfying instance. Okay, so so that is how the algorithm works. Okay, before I pose the correctness and completeness question, any questions about the way the algorithm works? Yeah, just to see the algorithm, you see. So you select the smallest basic variable such that either, which violates it. So the violation can be due to, the value being less than the lower bound or greater than the upper bound. So, and the fixing is very much dependent on how you do it. If it is less than Li, the value of the variable has to increase. In which case, then in order to pick the variable that the slack variable that you adjust, it depends on the coefficient value. If the coefficient is positive, then in order to increase it, you will have to pick the variable among the slack variable that is slack on the higher side, okay, because you have to reduce it. Or if the coefficient is negative, then you have to pick something which is greater than the which is greater than the lower bound, okay, and then you use that. And the dual of that is what happens if the violation is due to the value of the basic variable being above the upper bound. Okay. One other thing is the theta is one other point I had to mention is that theta is the adjustment is done such that it is made to so the fix will be as minimal as required, okay, so that it'll just if you increase it to get it to the lower bound, you'll only increase it as much as to get it to exactly the lower bound, or if it's decreasing, it'll think. So the fixed variable will, once it is fixed, will either be at its lower bound or its its upper bound, and that's how it is fixed. Okay. Yeah. So I'm assuming there's no questions. Are there any questions?
No, sir. It's clear, man.
Okay, fine. Then why the question? I think someone already asked it last time. Why should the such an algorithm indeed find a satisfying assignment when there is one at all? Okay, so that is the question, because especially we are choosing one variable at a time to fix. Based on the invariant, the two invariants that it preserves, that the slack variables always satisfy their constraints. And here the goal is that it, although it picks one basic variable at a time to fix, eventually, I mean, that as long as if there is a satisfying assignment for the set of constraints, and if the algorithm terminates, then since you know that when it terminates, it terminates only when all the basic variables are fixed so as to meet the constraints. So the correctness that indeed, if there is a satisfying assignment, it will indeed find one, is reduced to one of showing that the algorithm indeed terminates, because you know that when it terminates, it indeed has all the variables satisfying the thing. So central to proving the correctness is to show that it indeed terminates whenever there is satisfying assignment, because when it terminates, that it thing. So you will see that this thing is, the proof of this is fairly nicely done. The chapter in the book does not discuss the proof, I think, but the paper by for which I have given a reference later in these slides, and I will also upload that, has a very nice and nice proof of termination. Okay. And that's what I want you to read as a supplemental reading, and then enlighten us all. But I just wanted to make one observation about why, what exactly the termination proof involves. And if some of you, and as an exercise for a class presentation, I want you to go through that. And those of you who might have seen simplex algorithm in another context, in another course, if indeed there was an argument, I mean, a proof that you are familiar with, I want you to compare it with what is discussed in the proof that is discussed in the paper as well. So that will be useful to get an insight on. So effectively, the proof reduces to what can go wrong. Okay, so when you are, see, in this case, when for the choice of the variables that you did here, you went from A to B to to C. So, let's suppose that, and because that's what the ordering dictated. For any ordering, what could go wrong and make termination, that the algorithm not terminate, okay? And that is that maybe when you're still in the non-solution space that is outside of this shaded region, your choice of variables can end up moving back and forth between interminably back and forth between two non-solutions. For example, here, if I chose, so sir, here let's suppose once again. Yes, hello.
Yeah, so I think Harsh has gotten disconnected. Should we wait a couple of minutes? Or?
Okay, so we could.
Yeah. Sorry for interrupting.
The participants.
Amay, do you have his number or something? Can you reach him?
Yeah, I asked him, but no response yet.
Okay.
But Harsh usually doesn't have a problem with his internet. Devjit is the one that does have some problem, no?
Might be a power cut or something, not sure.
So Harsh right now is in the campus, or is he at his hometown?
I think he's at his hometown.
Which is where?
I'm not really sure, but I think somewhere in the north, but I'm not sure where.
Okay. And which part of Maharashtra are you in right now?
No, I live in Hyderabad, but
you live in Hyderabad. Okay.
Yeah.
Did you send him a message?
Yeah, but he hasn't responded yet, so I'm not sure.
You sent him you messaged him, or you tried to call him?
No, I messaged him on WhatsApp.
Maybe we could go on. So maybe before you meet, or before you start your part, okay, because this is just a preamble that I'm giving, okay?
Yeah, and I also realized that it's being recorded, so it's okay. Yeah.
So for example, what I was saying was, the termination, it could be a problem with termination if somehow it doesn't make progress each time that you pick another variable. I mean, you could, like I said, you could be, permanently circulating among points in the non-solution region. Okay, to illustrate that, so suppose you had chosen a different ordering. Okay, in this case, what happens is you first choose X to fix S1, and then to fix S3, because you choose Y, which happens to be the lowest ordering. But suppose in your ordering, Y happened to be at the very end. Okay. Then, in order to fix S3, once you do S1X, S1 gets moved to among the slack variable. So S2 is, so S2 is still a thing. So in order to fix S2 is satisfying its its constraints. So the smallest variable to fix would still be S3, which continues to its violation. So, but the smallest variable to choose in the ordering would be S1. So instead of S3Y, you would be choosing S3 S1. Okay, that is S1 to do it. So what happens is that's what you would do. And as a result of which, what happens is you move from A to B, and then with S3, S1, that moves you to D, which is the intersection of S3 to this negative region. Okay. So when you are choosing, things like S3, then what is the guarantee, you can ask, that from there you won't move to B again? Okay, that is, you move from A to B, B to D, and then you can be flipping back and forth between D and B forever, because after that you could do S3. When you do S3, S1, you will fix S3, but S1 gets violated. Okay, then you could be choosing S1, S3 again. Okay, and that is what in your proof you have to show that such a thing will not happen. Okay, and for that, the crucial thing is that every time that you fix that, in some sense, you will be picking a different kind of a solution point that is somehow moving closer to your thing, and there it is very important. So these two things, that you're fixing only the bare minimum that is required. So when you fix a certain variable and move it to the slack variable, it is right on that edge, that is at the lower end or upper end. And when you choose the next one, you see you're imposing it to be not, you're forcing it to be something that is greater than or strictly less than their bounds. Therefore, that somehow, that will prevent, once you choose S3, S1, that condition will prevent you from making S1, S3 choice, that is flipping that thing again, over. Okay, in this case, where there are no upper bounds at all, it is very clear. Okay, so when you have both lower and upper bounds, like I have shown, here, this is the example that I'm kind of using as an illustration. Okay, so if you're using, given this ordering, why can't this thing happen ad infinitum? Okay, with S3, S1, then back to S1, S3, and so on. Okay, and that does not happen. Okay, and your proof of termination essentially boils down to showing that such a cycle will not happen. Okay, given a particular ordering. So if once you show that such a cycle does not happen, although you do one at a time, you could see that the strict ordering on the variable, even when you have y much later, then you will eventually get to something which you need to adjust in order to fix it. And that's the argument that is given in the paper, and it does for an arbitrary multi-dimensional thing. So in order to understand, what I suggest is, in addition to reading the paper, just use this example that I've shown here, which I've published, for you to understand why. And that is where the condition that that is given in the algorithm that I showed you, where you pick the slack variable to adjust, is important, because as soon as you fix S3, it is fixed only as much as is required, and therefore when you do bring back S1, or when you fix S1 here, that is done, and therefore this is allowed, S3 to S1, but you you won't be permitted to do S1 again here. And the strict condition, inequality condition there ensures that such a cycle will not happen. Okay, I know that this will require some amount of thinking, for you to reflect on. So what I suggest is, for us to read that paper, okay, the proof in that paper, along with some examples for you to simulate. Specifically, this one I'm going to give you, which you can use as an aid to ensure that such repeated going back and forth will not happen. That you'll move your solution towards the region where you have the solution. The choice of the variable is forced in such a way that you move towards the thing. And that's where I want to end my portion. I mean, other than taking some any questions that you may have. Yeah. Okay, so we will revisit this. Okay, so I want you to, so I will make up what the requirement for your in-class presentation as follow-up reading, and I'll schedule that appropriately, and we will revisit this the thing. So that will make you kind of understand why simplex algorithm really works. Okay. Although you choose one at a time. Yeah. Okay, so if there are no questions, then I will stop sharing. Yeah. Yes. Okay. So one, although I know that ReluPlex, just a little bit of motivation for ReluPlex. That is not what Madhukar will discuss today. One point about ReluPlex that I will make, and I'll hand over. Okay, what we have discussed now is simplex, which works for the conjunctive fragment. In order to have it work for arbitrary Boolean combination of these atomic propositions, we've already discussed DPLLT. So DPLLT works with DPLL with the simplex theory. That is the generic way in which SMT works with any theory. So the motivation for ReluPlex is, rather than make it use SMT for working in using its generic framework of DPLLT, would it be more efficient to tailor simplex itself by moving the ReLU constraints into the theory of extend the simplex theory by beyond just being able to do the conjunctive fragment, like the conjunction of these things. Instead, that plus also make it understand the ReLU constraints and then do it. That is a specialized version of simplex, which extends it beyond the conjunctive fragment to take care of the propositional constraints imposed by the ReLU function. And if we did that, would that be more efficient than using a combination of DPLLT and simplex? That is the motivation for ReluPlex, and that's what Madhukar will discuss when he presents. That's the motivation for ReluPlex, which will be discussed later on. But today, in the interest of making, getting you the background required for you to start thinking about your project work, which will be on applying the verification techniques that we have learned so far. to RNN network, he will cover that the RNN verification as a priority. Okay, and then we will revisit ReLU-Plex. I mean, we will visit ReLU-Plex, not revisit, since later on, once the RNN verification is done. Okay, so with that introduction, I'll stop sharing and make Madhukar host and give him control. We can take over. Madhukar.
Yeah, yes, sir. So any word from Harsh? Do we wait for him?
No, I have not. I can send him an email.
Yeah, even he hasn't responded to me as well, so I don't know.
He has not, or he did?
No, he has not responded.
Let's go ahead. Okay,
Yeah.
Since it is recorded, and next time maybe when everybody is there,
I'll do a quick recap.
Yeah, you can do a quick recap and then ask questions. Yes.
Can you see my screen?
Yes.
Yes.
I can. Yeah.
Yeah. Is it too small, or is this okay?
I think this is big enough, and it's actually
this is fine.
quite good. Yeah.
Just so that I can write things.
Yeah. I think that's yes.
Yeah. Okay.
Big enough to.
Yeah, sure. Just give me one moment. Yeah, so as sir was saying, we will start looking at RNNs first, and then we will come to one of the very popular ways of verifying neural networks, for which special solver was designed, and that's what goes by the name ReLU-Plex. And we'll come to that. It's built on simplex, so that's why we looked at simplex. And so we'll come to that. So for today's talk, normally we would have wanted to cover that first, but since for our project we'll be looking at recurrent neural networks, let's look at this work first. But we'll come to that. So I think that there is in some part of the talk I'll be assuming that there is a way to verify feed-forward neural networks, and we know that, and then I'll come back and fill that gap. Okay. So yeah, so this is a paper by these guys. So these are the authors of the paper, and this is a recent paper. I think this appeared in ATWA 2020 or 2019 or some such thing. Okay, so this is a very recent paper. In fact, this area has gained a lot of interest in the last several years, maybe 5 years. Or I mean, of course there was work even earlier also, but there has been a lot of work in the last 5-7 years. And so therefore this is a very recent area in general, and therefore the papers are it's not that the whole thing has evolved too much, so you can still read a paper without requiring a lot of prerequisite, and most of these things try to adapt verification concepts in the area of deep learning to verify that a network is behaving the way we would want it to behave. Okay, yeah. So let's look at what recurrent neural networks are. So these are a particular kind of deep neural networks, where you have a loop of this kind. Like you can see that there's an arrow going from this node or neuron to itself. Okay. So of course, this is not the. I mean, there are feed-forward neural networks where you don't have such arrows. The typical kind that you see. I think I have a picture somewhere later, or yeah, maybe not in this slide deck. But But yeah, feed forward neural network is, something that you see that you have neurons in each layer, and then you have arrows going in only one direction. So you have these kind of arrows only going in one direction. So these are called feed forward neural networks. And here we have a neuron in which there is a loop. Okay, so these are RNNs, and we'll see why these loops are important, or what is the semantic sense that these loops make, and so on. Okay. So yeah, so we study RNNs because they're suited for some tasks like machine translation, speech recognition, and these kind of things. And we'll understand why they are suitable for these tasks. Okay, and as we have as I was saying earlier, that when you build a network to do something, you want to be assured that it is doing the desirable thing, or it's not doing anything undesirable. And this is the same thing as is the case with programs. When you write a program to do a certain task, you want to be sure that the program will do the task and will not do anything undesirable in the process. Okay. And what I mean by vulnerable to adversarial inputs is that these are networks typically large in size, and you have multiple layers where there are multiple neurons, and then there are these edges and weights. So I mean, I'm assuming that you have some background in this thing. I'll define these things formally, but so you have these large networks. There are neurons feeding into each other, and there's a lot of multiplication, addition happening. So while you are expecting some output for something, you change some value or some weight of some edge in between, and things change drastically. Suddenly there is an image that was being classified as a cat earlier is not being classified as a cat anymore. Or you can see that you've seen, I'm sure you've seen these examples where you take an image and you add some background noise to it, and it visibly doesn't change the picture, but the classifiers of course are not able to predict that predict which class it belongs to anymore. Okay, so there is a need to formally verify when you build a network to do a certain task. You want to formally verify that it will do the task, or it will not do anything undesirable, and that's the kind of setup that we have. And in fact, this is what we'll talk about when we are looking at feed-forward neural networks, ReLU-plex, or even when we are looking at a few other things, if time permits, about verifying RL systems and so on. Okay. So first of all, again, once again, I'm assuming some background, but let's not worry about that. So the point that we want to make first is that if you have a network of this kind, if you have a loop, then at least for a network, and it holds true for a program also, that you can do an unrolling. So this thing goes from this one to itself. So you can actually do it.
Madhukar, so yeah. I think they have seen that, okay, because I did cover even bounded model checking of loops with the thing. If that's the background that you were unsure about, so I think that they have seen that, and I hope, Ameya. So this is, I think that's what you mean. That's what you mean, right? So the unrolling part to deal with loops, they have seen. Okay, and Ameya, and that's what I think Madhukar is referring to. And if you,
Yeah, so I think I'm familiar with this. So actually, I have learned RNNs in another course as well. So
okay.
It should.
But I guess you have learned RNN, which is good. But from the point of view of probably how they are designed and how they work and so on, which is actually good. That gives you insight into the way it is trained and so on. But here he's talking about from the point of view of verification, I guess. Yeah, but that's still, that background would be good. Yeah,
sure. Yeah, one more thing, I don't think I can see chat messages. Sorry, I don't think I can see chat messages. So if there is any question,
I will do that. I think so far there's nothing there.
Or if one of you has a remark, you can simply unmute and say it out instead of typing it. Yeah. Okay. So so the point that I was trying to make here is that if you have if you have a network of this kind, it has a loop. It has a loop, and then you can actually unroll this thing like how you would unroll loops in a program, right? So you can do an unrolling. So this shows that this network has been unrolled 3 times, and remember that you had the V's feeding into V's. So you have arrows of this kind, and then you had sorry, these are not all of these are V1, these are X1 and copies of X, and these are copies of Y, which is the input and the output. But the point that I'm trying to make here is that these things can be unrolled, and now you can have more copies depending on how much you want to unroll. And now you will only have arrows going in a forward direction. So these are, again, you can unroll them into what are called feed forward neural networks. Okay. And although we have not seen how feed forward neural networks can be verified, I think Diganta may have shown you small examples where you can take a network and encode the constraints into an SMT solver, and then you can call some solver. Maybe he experimented with Z3, so you can call Z3 and you can find out if a given network satisfies a given property or not. So you can do this. He would have shown you some examples, and I'll revisit those examples when I'm talking about the verification of feed forward neural networks. But here what we want to say is that if you have an RNN, then you can do an unrolling, and now you'll get a feed forward neural network. And assuming that you know how to verify them, you can actually verify an RNN by doing this kind of an unrolling. Okay, so except that this is not suitable, because once you unroll this thing, you have your network becomes much bigger in size, and the complexity of this feed forward neural network verification is exponential in the size of the network, and therefore it's not a good idea to increase the size of the network, because then you're increasing the exponent. Okay, so this is not this is something that can be done, but it's certainly not a good way of doing it. Okay, so let's take a simple example to understand this thing slightly better. So you have, this is a very simple example, and so you have this RNN where this is the input. This is this is the only hidden layer with the only hidden neuron, and this happens to be what are called memory neurons. So there is a loop from this to itself. Okay, and this is the output layer. So there's only one neuron in the output, and for simplicity, we have the this is taken from the paper, so they have kept the edge weights as 1. Okay, so the only thing new or different from a normal network is that there are these memory neurons, and then there is a loop. So you store the value, whatever value is computed is being stored, and in the next iteration you try to reuse this value by having this memory block. So we'll call this the memory block. So the memory block feeds into the neuron. Okay, so let's see how this behaves. So we'll see how this network behaves for 4 time units. So I'm interested in looking at the behavior of the network for 4 time units, and at each time unit I will get a different input. Okay, so this will keep consuming inputs as they come along. So I'm interested in inputs of length 4, or inputs that come at 4 successive time units. Okay, so at the first time unit, let's say you get an input of half. So when you get an input of half, this half travels along this edge. So you get half times 1, and there's nothing in the memory. So there's 0 in the memory. So there is nothing that you get from this edge. Okay, so you get half at this particular neuron. The value that this computes is half. And then similarly, because this is half, and okay, yeah. So one of the things that I didn't mention is that the hidden thing implements a ReLU activation function. So whenever the value that you compute here is greater than 0, then you keep the value. If it's less than or equal to 0, then you make it 0. Okay. So and this is the activation. So this is the ReLU. It implements a ReLU activation function. So yeah. So you get half from here. You get nothing from here. So you get the value that's computed is half. When ReLU is applied on half, you keep the value. because half is bigger than 0, and therefore the value that the final value here is half. And therefore this half travels along this edge of weight 1 to this output, and the output does not have any activation function, so you get half at the output. Okay, so let's see how this evolves. And so in the next time unit you get a different input, so you get 1.5. So you okay, yeah, so one of the things that I didn't say, that this half that was computed here is stored here, is sent here. Okay, so you store this the last value computed in the memory block. Okay, so now next time when you get a half from here, so you next time when you get a 1.5 from the input, then you get 1.5 from here, and remember that there was a half here, so you get the half from here. So overall you will get 1.5 plus half, which is 2. 2 is bigger than 0, so you'll continue to send 2 across this line. Okay, so which explains the 2 here and the 2 here and the half from the memory. Okay, and now since we know how to do it, let's take some more inputs. At the third time unit you get -1 from here, so you get -1 along this edge, so you get -1 here, and remember that the last time the value was 2, so 2 was stored here, so you will get 2 from here. So this 2 will come from here, -1 has come from here, so together it becomes +1. Since +1 is bigger than 0, we'll keep +1, and then the same 1 is sent along this line, so you get 1 and 1. And remember that 2 was available from the memory earlier. Okay, and now when you get -3 from here, you get -3 here, and 1 was available in the memory, so you get +1 from here. So overall it becomes -2, which is less than or equal to 0. So therefore it becomes 0, and then 0 travels along this thing, so you get 0 at the output. Okay, which explains all this. Okay, so what we have seen here is that if you have a recurrent neural network, then you can talk about a stream of inputs. And in fact, it is for this stream of inputs that, and this stream can be of an arbitrary length, and that's why you don't have a you need an RNN. You don't have a, if you had a fixed length thing, if you knew the number of inputs, then you could have a feed forward neural network. But to be able to handle a stream of inputs, you take an RNN.
Excuse me, I just have a small doubt.
Yeah.
So when you're sending from V21 back to the previous time step, you're doing it after applying the ReLU function, right?
Yeah, it's the value, it's the final value computed.
Okay, yeah.
Okay. Okay, so you can, so this is why this is interesting, right? So you can now talk about a stream of inputs, and you can talk about variable length inputs, because some input can be of different length, other inputs can be of different length, and therefore these things make a lot of sense. Okay, but notice that if you have to analyze this, then you will typically know the size of the input, and therefore you will be able to do an unrolling and analyze things, unlike in a program where you don't know the amount that you have to unroll. Okay, so in programs, typically the amount that you have to unroll depends on the value of some variables, which you will not know until it cannot be decided upfront. So therefore it's slightly different in that sense. Here an unrolling can actually be done always. Okay, there you cannot always do an, yeah, sorry, is there a question? Hello?
Yeah, no, not from me.
Okay, and I think you're the only one there, right? Or has somebody joined?
No, I think I'm the only one right now.
Yeah. Okay, yeah, sure. So yeah. Okay, so unlike so I said that this is similar to a program, because in a program also you can unroll, here also you can unroll. The way it is different from a program is that in a program you don't know the amount that you have to unroll. Here you know necessarily the amount that you have to unroll. It's just that unrolling is fine, but the verification is exponential in the size of the network, so you want to avoid unrolling. Okay. Now let's see what an RNN verification query may look like. Okay, so if we take this network, we may be interested in verifying some properties. So let's take one property of interest, and so the property that I want to verify is that if the input always remains between -3 and 3, okay, then the output, okay, so if the input always remains between -3 and 3, and I'm looking at input sequences of length 5, not more, then can the output, will the output always be less than or equal to 15? Okay. Okay, this is the question that I want to ask, that I want to look at 5 length inputs. I know that the inputs will always be between -3 and 3. So this first column here will always have values between -3 and 3. Then will it be the case that the output is always, does it imply this, is the question. Okay, so let's look at, what this verification query formally looks like. So you have, there are 3 parts to a, so there are 4 parts to an RNN verification query. One is a precondition, which is the condition that you have on the input. So in our example, as I said, the precondition is that all inputs will be between -3 and 3. Okay. Then there is a network, which is the RNN itself, this entire thing, the network that you have been given along with the edges and the weights. And then there is this post condition. The post condition says that, remember that the property that you wanted to verify was that the output will always be less than or equal to 15. This will be violated if the output is ever 16 or more. And that's why we want to see whether it is, if at least once it becomes greater than or equal to 16. Okay. So this post condition is the negation of the property. Okay, and then the time duration for which the property should hold. So remember that, we had this 5, we want to look at sequences of length 5. Okay, so these are 4 parts to an RNN verification query. Okay, so I think I should relate it to, how this verification queries look for feed forward neural networks or for programs. So in feed forward neural networks, you don't have this component because it's a fixed thing, right? You have the input layer, you have the output layer, you have the hidden layers in between, and you can talk about a precondition, which is some condition on all the neurons in the input layer. You want to specify a post condition, which is about the neurons, the value of the neurons at the output layer, and then you have this network in between, which has all the weights and the biases and the connections. Okay. So for a feed forward neural network verification, this is what the verification query looks like. So you will have a precondition, you will have the network, and you will have a post condition. Okay, this is an additional thing that we have in case of RNNs. Okay, and this is what you have a typically this is the structure that you have even for program verification. You have a precondition, you have the program, and then you have some post conditions. So there is a pre, there is a post, and you want to, and then there is a program in between. So if I'm sure you would have seen Horde triples, which have this thing that there is a pre, there is a statement, and then there is a post condition, and in instead of one statement you can have multiple statements, and instead of multiple statements you can have a program and whatever. But the idea to the concept of verifying a network or a program with a pre and a post condition is known. It's common to formal verification. Okay, so this is what a verification query looks like. Okay, so once you have a verification query of this kind, notice that the max time duration for which we wanted this to hold was 5. So, and you knew this upfront, so you can actually do an unrolling 5 times. Okay, so these are the inputs, these are the outputs, and these are the 5 hidden layers. Sorry, these are the 5 hidden neurons. Okay. And so you have done this unrolling for 5 times step. This is something that you knew, and now you have these additional edges between this thing, because you had this, the memory was feeding back into the neuron with an edge weight of 1. Okay, so here this is similar as the last one. Here also, the previous value feeds into the current value with an edge weight of 1. Okay, so this is what it looks like, and now you have a feed forward neural network, and now you can verify it using Reluplex or any verification technique that verifying FFNNs. Okay, we don't know it now, but we'll look at it. Okay. And the only problem, of course, is that, earlier you had three neurons in your network. Now you have 15 neurons in your network, which is not a good thing. Okay. So I tell you one way of verifying this thing, one way of verifying RNNs, and then we'll see what is good about it, what is not so good about it, what is it that can be done. Okay. So one of the things that we'll do is, we will still try to change the problem of RNN verification to feed forward neural network verification. So we'll still try to do this thing. We'll still try to model this problem as this problem. Okay, this is what we want to do. But we want to do it without unrolling. So this is a way of doing the same thing, but with unrolling. We would like to try something without unrolling. Okay. Because, and why are we interested in this? Because we know how to solve this problem. Okay, so we know how to solve the feed forward neural network verification problem. So we can, sorry. Okay, so we know how to solve this problem. So we can transform this into this. And if we can do that without unrolling, then that's great, because the solution that we know of this problem is exponential in the size of the network, and therefore we would like to get as small an FFNN as possible. Okay. So here is another transformation of the same example that we had seen. Okay, here is another way of transforming this thing. Okay, so there are 2 or 3 things that we have done here. Okay, so one of the first things that we do is that remember that what was the earlier thing looking like. So you had this V11, and then this was going to V21, and then going to V31. Sorry, except that here it was feeding it back to okay, V21 memory tilde, whatever it was called. Okay, so here now, so we are, once again, we are trying to do a transformation so that we can change this problem into this problem. So this is what we are trying to do. So one of the things that they say that you can do is you can pull this memory block, this square block, out to the first layer, wherever it is. There could have been another hidden layer here, and there could have been a memory thing here. Okay, and so on. But they say that, look, wherever your square blocks are, you just pull them out in the first layer, wherever, however deep in the network they may be, you just pull them out in the first layer. Okay, and then you maintain the solid edge which was feeding into the neuron. So you maintain the solid edge. So here 21 had a memory node corresponding to it. So you pulled that 21 memory out here, and you have maintained this solid edge of 1. The thing that is missing is this dotted edge, which was feeding the previous value back into the memory. So whenever a value was being computed, it was being fed into the memory so that it can be used later. But now you don't have this. You don't have the dotted thing. You only have the solid thing, and you do it from from every layer. So even if there was something here which had a memory thing, then you maintain this thing, and you have edge weights, whatever is the weight. Okay, and as deep as possible, but you have all these things. So you collect all the memory neurons in the top layer. Okay, so let's see how is it affecting the value being computed. Remember that this is fine. It can, if we knew these values, if we knew what these values are at any point in time, then these values will be fed into the neuron rightly, because you have preserved the edges that fed into the thing. Okay, so from here, the edges that fed into the neuron have been preserved with the exact same weight. So if we knew that these values precisely at this point, at the input point, because remember that this is the input layers, and you have pulled all of them at the input layer. So if you knew these values of the neurons that we had pulled out, then the value being computed, the output will not change at all. Okay, so this is one of the things that they do. Okay, and also remember that now this is not, it's not the most traditional feed forward neural network that you see, because in the traditional FFNNs or in the standard FFNNs, you only have edges that are one layer, that go from one layer to the next layer. You don't have edges from this one going to this one. Okay, but here you have edges from here going all the way to here. Okay, so this is the only difference from feed forward neural networks, but this will not affect us in any way, and we'll see how. Okay. Okay. So just to understand, we were trying to transform this problem of RNN verification into feed forward neural network verification, and we were trying to do it by doing transformation of the network. One way of doing it is by unrolling, and right now we are trying a different way so that we can avoid unrolling. Okay. So in that one, we pulled out the memory neurons at the top layer. Okay. And now we have added one more neuron without any edge to anything for the time. Remember that, this was whenever we had this property, we had the time thing, which was important. In fact, this is the value that gave us, that told us how much to unroll. Okay, so, and it's a part of the verification query. The time is given to you as a part of the verification query. So you make a neuron for time. You don't connect it to anything, but you just keep a neuron for time. Okay, and this is all that is there to this, this problem being transformed to this thing. Except that remember that all these things that you have pulled out at the memory thing, now you don't know, because you have eliminated all the dotted edges that fed back into the memory. You don't know the value of these things, so you don't know the precise value of these things. Okay. Okay, and this is the information loss that has happened. Okay, earlier, when you're doing unrolling, there was no information loss happening. This was precise, but now you suffer from a loss. Okay, because you have not increased the size of the network, so there is some there's some payout, and this is the payout is that you suffer from some loss. You're not able to. Okay, now let's try to minimize the loss that we have suffered. Okay, so what is one way of minimizing the loss that we have suffered? The one way of minimizing the loss that we have suffered is to guess these values. Remember that now these are at input layer, so these values have to be available at the input. Okay, so let's guess these values as precisely as we can. Okay, if we are able to guess these values as precisely as we can, then we would have minimized the loss. Okay, so this is the idea that goes behind this paper. Okay, so they do a transformation where they pull out the memory neurons, and then they will try to predict it as close to the real as possible. Okay, and by as close to the real as possible, I mean two things. First of all, of course, it has to be as close to the real, and it has to be close enough to be able to verify the property that we are trying to verify. Okay, so we are trying to verify that the output should not be bigger than or equal to 15, and we want to somehow find some constraints on these memory things which brings it close to reality, and also perhaps if this property holds, we would like to verify this. So that's roughly the idea behind this thing. Okay, so once we have changed this RNN verification problem into a feed forward neural network verification problem, let's understand what formally what it looks like. So earlier you had this RNN, now that has been converted into this network. Okay, which I claim is a feed forward neural network, except for these memory things which can go as deep as in the thing as possible. Okay. Okay, but other than that, it's a feed forward neural network. So let's call this this new network NHAT. So we have remember that when I had talked about an RNN verification query, I had told that this Tmax is an extra thing, but even for feed forward neural networks, you have a precondition, you have the network, and you have a post condition. Okay, so the network, of course, has been modified. So we have seen how the network has been modified. Let's see whether the pre and the post conditions have to be modified so that we can talk about the same problem in the new network. Okay, So the post condition does not have to be modified. The post condition remains the same because the output, there's nothing that we changed in the output layer. So the post condition remains exactly the same. So we still want to check whether it is possible for v3, 1 to be bigger than or equal to 16. Okay, so the post condition does not change at all. The network changes, of course, as we explained in the construction. So this is the new network. Let's see how the precondition changes. So remember that, this was the original precondition, that all the input values will lie between -3 and 3. And this made sense because earlier this was the only thing in the input layer. So the only neuron in the input layer. Now you have added all these memory neurons, so we should talk about them. And you have added a time neuron, so we should also talk about this. So your precondition should change. Okay. So your original precondition certainly continues to remain one of the preconditions, but you should add additional preconditions to account for the values that these guys can take. Time, of course, can take values between 1 to 5. Okay, because 5 is the max time thing and 1 is the minimum. So time can take any value between 1 and 5. Okay. And now, okay, so you have constrained this one. So the only thing that you have not constrained is these memory neurons. Okay, so you must find a constraint on the memory neuron. Okay, so this is something that we need to find. Okay, we need to find a constraint on the memory neuron, and this can be anything. You can say that, look, your memory can take any value. Okay, or your memory can take a fixed set of values, or your memory can take only so many values, or it depends on other things like t and whatever. But the point is that we want to put some constraints on it, so that if the property held in the original network, then it should hold in this network also. Okay. So this comes from the original precondition, this comes from the time, the post condition comes from the post condition, the n hat comes from the construction that we have done. The construction has only 2 parts. You pull out the memory neuron to the first layer, you add a neuron for the time. Okay. So all the other 4 things are very clear here. We just don't know how to constrain these memory neurons. Okay. And we'll see one way of doing this. So at this point, I'll maybe I'll stop and ask if there are any questions.
No, everything is clear to me.
Okay, and you're still the only one.
Yeah.
Okay, sure. So this is fine then. So let's okay. Yeah. So I should also give some background on inductive invariance, because inductive invariance is what we are trying to what we'll try to use for this this thing. Just 1 second. Give me 1 second. There's a call that I need. Yeah, sorry. So we'll look at this this concept of inductive invariance. Now, some of you may have seen this, but let me go through anyway.
Yeah, I think they went through this, okay, because they have already working on loop invariance. I mean, I covered loop invariance and so on. No?
Correct. Yeah. And there's an assignment that is.
Yeah, that's right. So you could recap it in the form that you want to do it, but you may want to go. It's okay to go quickly also.
Yeah, certainly. So I'll go through this quickly. Okay. So consider this program that you see on the left. So you have x and y, which are both 0 in the beginning. Then in a loop for some arbitrary number of times, you increment x by 1, and then you increment y by x, and then you want to assert that y is greater than or equal to 0. Okay. So the way we would like to do this is by getting an inductive invariant for the loop. Okay. So an inductive invariant for the loop is something that, as Sir would have explained earlier. So an inductive invariant for the loop is something that holds at the beginning and then it holds subsequently after every iteration. If it holds at the beginning of the iteration, then it holds at the end of the iteration. That's the idea. Okay. So for instance, we would like to check whether x is greater than or equal to 0 is inductive or not. And it is inductive because, x is x is 0 in the beginning, which is greater than or equal to 0. And whenever it is greater than or equal to 0, you add 1 to it. So it will continue to be greater than or equal to 0. Remember that, we are not worried about integer overflows and so on. We are talking about mathematical integers. Okay. So this is inductive. Okay. So x greater than or equal to 0 is certainly inductive. Okay. We would also call an inductive invariant safe if it can imply the safety property, but x greater than or equal to 0 cannot imply that y is greater than or equal to 0. Okay, because it cannot, right? Implication, we know how implication works, and x, by knowing that x is greater than or equal to 0, you cannot determine that y should be greater than or equal to 0. Okay, which is what I mean by but not safe here. Okay, so I'll call the interesting inductive invariants are at least for the purpose of verification, we'll call them safe inductive invariants. And when we say inductive invariants, we would many times mean that we are looking for safe inductive invariants, something which is inductive but is also strong enough to prove safety. Okay. Now let's look at another expression, y greater than or equal to 0. Y greater than or equal to 0 is safe because it's certainly, if you know y is greater than or equal to 0, you can certainly prove that y is greater than or equal to 0. But it's not inductive because, if you, it holds initially certainly, because if y is 0, then you know that it's greater than or equal to 0. But if you knew that y is greater than or equal to 0 and then you added x to y, you cannot say that y will continue to be greater than or equal to 0 because you don't know what x is. Okay, so therefore this is not inductive. So therefore you need invariants that are both inductive and safe, and there are invariants that are both inductive and safe. In this case, for instance, if you know both that x and y are greater than or equal to 0, then you have something which is inductive as well as safe. This is not the only invariant. There are other invariants which are inductive as well as safe. This is another example, which is an inductive as well as a safe invariant. Okay. And as I said, and I'm sure you've seen this earlier also. So there are three parts to the whole thing. The first thing is that there is an initiation that should hold, so it should hold at the beginning of the loop, and then there is a consecution part which says that if it holds, and if you go through the loop body once again, it should continue to hold. And of course, it should be strong enough to prove that the assertion holds, or the negation of the assertion is not reachable. Okay, which is what I denote by safe here. Okay, so we want these three properties to satisfy: the initiation, the consecution. The initiation means that it holds initially. The consecution means that if it holds at the beginning, then it holds at the end of an iteration. And safety means that it's strong enough. Okay, and this is just formally I'll upload these slides so you can check that these properties hold for this program and those candidates that I was showing earlier. Okay, so now one of the things that you can do with your RNN, remember that your RNN was what it was. I should carry the picture here, otherwise I'll keep drawing. But anyway, the point is that it's a simple thing. So this was 1 1 1, and this was the 11, and this was 21. This was 31. I'm writing the v1 comma 1 as 11, v2 comma 1 as 21. Okay. Okay, so these are the things. This was the 21 memory, and this was the network. So now, if you have been given such a network, you can write it as a program with a loop, right? Except that the loop will have a known bound because you knew that t is less than or equal to 5, because your 5 was the max time unit. So you can code this up as a program, because what's happening really in a network anyway, every network can be written as a program with with if then else, and with some computation, the multiplication, the addition, the activation function. Okay, so it can all be written up as a program. So you start with so you have real variables. So your t is equal to 1 in the beginning, your memory has 0 in the beginning, and then you have these real variables for the values being computed at every neuron. Okay. 11, of course, is the output, which can be anything, but you have a precondition that forces it to be between -3 and 3. So therefore, there's a corresponding assume statement that we have saying that, V11 has to be between -3 and 3. Okay. Now, once you have V11, you know that 21 is nothing but 11 plus what you get from the memory. So V21 is 11. It's actually V11 into 1 plus V21M into 1. But since these edge weights are 1, I'm just ignoring them. Okay. So V21 is V11 plus V21 memory. And now there is this activation function ReLU that has to be applied on it. So therefore, I have this if then else statement which says that if V21 is less than 0, then V21 should be reset to 0. If it is greater than or equal to 0, then we don't touch it. Okay. And then, of course, whatever you compute here should be stored back into the memory. So this is the statement that stores it back into the memory. And then 31 gets the same thing as 21 because they are connected by an edge of weight 1. Okay. So 31 becomes 21. And then you want to assert that 31 is less than or equal to 15 always. This is the property that you. Okay. Remember that, the post condition was the negation of the property. So therefore, the post condition was that for one of the instances, this should be greater than or equal to 16. Okay. Okay. And the property is that for all the instances, the output should be less than or equal to 15. Okay. So now you have been given such a program, you can actually do a program unrolling and you can verify that this this property holds true. But there's another thing that you can do, given this program, you can also get an inductive invariant and then prove that this property holds true. Okay. So I'll give you an inductive invariant. So, and then we'll check that, this is, or maybe, you can check that this is inductive and then you can see how it can help you prove that. Okay. So this is an invariant that I claim that is inductive. So V21M is less than equal to 3 times t minus 1. So before that, V31 is less than equal to 15 is also an invariant because, because no matter, what V31 gets, it gets a value which is less than or equal to 15. So it's an invariant. It's just that, it's not very useful to us because we cannot prove that it is inductive. So you can get invariants, but as long as, you can guess certain invariants, but if they're not inductive, they're of no use to us. Okay. So we are looking at inductive invariants because we can establish that, this is actually an invariant. Okay. So V21M is less than equal to 3 times t minus 1 is an inductive invariant. So you can actually check this. You can say that you can check that if this holds. First of all, you can check that the initiation property holds. The init holds because V21M is 0 and t is 1. So 0 is less than equal to 3 times 0, 3 times 1 minus 1, which is 0 is less than equal to 0, which is true. Okay. So it holds in the beginning. And then you start with V21M, which is less than equal to 3 times t minus 1. And then you do this entire computation and you can check that, the value that you have in the end is again less than equal to 3 times the new value of t minus 1. Okay, so you can check that. This is a very simple exercise. You can check this. Okay. So given such an inductive invariant, we can prove that this property holds. Okay. Okay, and this is what, of course, there are two things that I'm skipping here. One is, how did we know that this is an inductive invariant? As in, how did we find this out? And if somebody told us, let's say, then how can we check? So there is this thing of finding or guessing, and then there is question of checking. Okay, so so I'm avoiding these questions for now. I don't know how I landed at this, and I there is this step of checking that this is an inductive invariant, which for this program, at least, I'm claiming that you can check because.
Yeah, but I think they have gone through this actually as part of the exercise, at least for a program, given a program.
Correct.
How they need, what they need to do to check.
Correct. Yeah, so that's what
covered. Yeah, as it applies to the network in terms of neural network, how do you do that? Correct. Yeah. As a program, that's what I want to make sure. Ameya, so in your assignment also, you have done this for a given program, correct? Okay.
Yes, sir. Yeah.
Okay.
Yeah. So that's what. So there are these two questions that I've avoided. Checking, of course, is something that you understand for this program. Finding, how who told us, or how did we find this, or I mean, how can we guess such a thing? And so this is something which is not yet clear, but I'll come to this.
Yeah, but manually, I think as a human being, you can guess it. I mean, automatically trying to do it. That's the difference that you're trying to draw. Huh?
Correct. Yeah.
I mean, if you're smart enough, I mean, as you could just like, I mean, how do you guess loop invariance? Okay, so how do you construct loop invariance? And human beings are able to do it. It's just that automatically trying to do it is an undecidable problem. Okay, and that is where the challenge lies.
Okay. Okay. Yeah. So there are, yeah. So this is the thing, right? So given if you had this RNN as a program, then we could have verified this program itself if we knew this this inductive invariant. Okay, that holds for this loop. Okay, if we knew this thing, then we could have verified that program. And the point that I'm trying to make here is that so therefore this is an important thing. If you really don't want to do an unrolling, then you cannot avoid this step of trying to capture what's really happening in the loop. And one way of doing that is to get an inductive invariant which is good enough to prove this property and capture really what's going on in the loop, at least capture that part which is relevant to proving the property. Okay, so therefore this becomes an important step. And so here, this V21M is less than 3 times t minus 1. This is an inductive invariant. And now if you come back, okay, so this is this thing that I had said, that it's there's something that we need to find here. This precondition was on the input continues to be a precondition. The precondition on the time is very simple. It has to be between 1 and 5. But there's something that we need to find about these memory neurons. Okay, and it's whatever, I mean, the goodness of this what we find, it determines whether we will be able to discharge the property or not, whether we'll be able to prove the property or not. Okay, and this is related to the task of finding an inductive invariant. Okay, so yeah, so that's all that I mean, of course there's more to this. I will get into the so when we meet tomorrow, in the next class, I'll go through this exercise of what it means to find it and what it means to check that it is an inductive invariant. Here, of course, for a program you can check, but the claim is that for a neural network you can, or for an RNN, you can pose the problem of checking whether something is an inductive invariant as a feed-forward neural network verification exercise. Okay, so you can pose the checking part as a feed-forward neural network verification exercise. Still, the guessing part, or how do you construct the construction, or the guessing part, is still not clear. Okay, and we will see that one way of doing this, and it holds true for programs also. So one way of constructing is to actually guess. You guess whether you try to guess. Okay, so you can construct an expression with some elements, or you can learn how to make smart guesses, and you can construct an expression, and then you can check whether it's an inductive invariant. If the check fails, then you construct another expression, and you can keep doing this. So in fact, this is something that works even for programs. Even for programs, if you want to find inductive invariants, you can do this guessing and checking method. Checking typically is easier because you're because that you're only talking about one iteration of the loop, so there are no loops involved, so it's a bunch of statements. Okay, certainly in case of programs. And in case of neural networks, we'll see how it can be posed as a feed forward neural network verification exercise. And checking, remember that checking, there are two parts to it, right? So you must check that the initiation holds, and the consecution holds. Okay, so we'll see how this checking can be done, and then we will try to see how to do guessing. So typically one way in which guessing works is that, you fix a template or a grammar. Okay, so you can say that, look, I'll guess expressions where there is a variable multiplied by, variable plus minus variable or something, or, you can have expressions of this kind. You can have expressions of variable is less than equal to constant times variable or something. So basically you can guess a template or a grammar, okay, in which you can try and construct different expressions by replacing this variable with all the variables that are there, x, y, w, z, whatever. Okay, so you can have a template or a grammar in which you are guessing, and once you guess, you can do checking, and with the guessing and the checking, you can get your invariants. And if you get good enough invariants, then this is the most critical part of verifying this thing. The rest of the thing is pretty standard. Okay, so we have also not talked about how to do feed-forward neural network verification, which we will look at in the next class, and we will see how that FFNN verification technique can give us a way of checking, and we will see what is a good way of guessing. So we'll complete the story along with the feed-forward neural network verification by ReluPlex. So we'll complete this entire thing in the next class. Okay. This is what I wanted to.
Yeah, I think in terms of the sequencing of the lectures, so you complete, okay, your discussion of RNN, okay, verification, and the 3 points that you mentioned, including the guessing part. Then before you do ReluPlex, is what I'm proposing, that Diganta will cover the nuts and bolts of RNN, okay, as to how a little bit of how they are used and trained and so on, okay.
Yeah, certainly.
Then you will cover ReluPlex, so that I mean, even I'm assuming that we will introduce the project, okay, problem, so that they can be thinking about that RNN, okay, corresponding to the application. So which will take one more class. I'm assuming that in the next class you will recap and then do the leftover part of RNN, how you encode the checking part as an feed-forward neural network verification, and the guessing of invariance, a little, how much you want to cover. Following that, the project introduction and RNN, okay, introduction. After that, ReluPlex. Yeah.
Yeah, certainly.
Is that okay?
Yes.
Yeah. That is completely fine.
Yeah. Okay.
Excuse me, I have a doubt in this thing.
Yeah. Tell me.
So if here, if your program is not, if that verification condition is indeed not true, like if it's not true, then how do you, like, any invariant will not
correct
right?
Yeah. So then, so this is, so remember that, if it's not true, then so what we are doing, what are we doing here? So here, when we pull these neurons out to the top layer, we are losing the information that was being fed back, right?
Yeah.
So we have lost this information, and without really reconstructing or regaining this information, we may not be able to prove that, the property does not hold if it does not hold.
Okay? Yeah, because in the guessing process, you'll just keep guessing and you won't get anything.
Correct. Yeah. So whenever, so therefore, and this is usually the problem whenever you're losing information, whenever you're losing some information to create, to create a shorter problem, to create a smaller problem. This is the step which is typically called abstraction in this literature. So whenever you're doing an abstraction, you are losing some information in order to get a smaller problem. And if the property holds, it is fine. If the property does not hold, then you may not be able to say.
Yeah, but a constructive way of doing it. So this is like pointed out, even in over approximation, when we are over approximating, that then if it doesn't hold, then you don't have a conclusive answer. But there are ways, practically speaking, to handle that. Okay. You may not get a complete solution, but there are practical ways to handle it. And that is to look for a first, you have to check if the failure to prove is due to your inductive invariant not being adequate or strong enough, or how Madhukar defined as it may not be safe enough, okay, to prove the property. That you can actually check, okay, by looking at maybe the counterexample and so on. First, anyway, there is that determination whether it is really an error. Suppose you don't, the verification condition checking fails. You'll obviously get a counterexample, okay? And maybe you can use that counterexample to see if it's a real error. If it turns out to be a real error, then you know that there is a bug. Here I'm suggesting, okay, admitting, like what Madhukar said, that it is not a complete way, you don't know, you have an inconclusive proof. There are practical ways to move you towards a solution, okay, verification. That is what I'm trying to explain. So there, you could first check, reason for the failure for you to prove, and that can be done by looking at the counterexample that you get, which can be what the error witness that the SMT solver gives you. Check if it is a real error. If it turns out to be a real error, then you know that it is that is the case. Otherwise, if it is spurious, that that does not occur, I think then you know that your inductive invariant is what you have guessed is not strong enough. Then you will have to look for a different, a stronger inductive invariant. So that is what is, we referred, but we did not get into. So in the case of when you abstract, like what Madhukar pointed out, you have to refine that abstraction. The lost information, you have thrown away more information than required for you to prove. Therefore, you have to look for a more precise abstraction, which is what in inductive invariant it means. You have to look for a stronger inductive invariant. Okay, so then you'll have to go through a better guessing process.
Yeah, and we'll look at a couple of in the next few lectures. I think this thing will come up a few times where we will see how we can see, even when a guess fails, you need to make a better guess, right? So there is some information that you expect which will help you make a better guess, and that information can also help you maybe understand what is going wrong, so that you can regain some information. And we'll talk about these things. So we'll talk about trying to regain some information, and may not be in this context, but in a different context, and even in this context we'll try to talk about these things. So tomorrow when we talk about how the guessing works and how you can guess better, we'll also talk about some of these things that sir said about trying to regain some information and prove that a counterexample is spurious or real or something.
Yeah, I think it's getting late for you, isn't it, Madhukar?
Yeah, I have a meeting from
Yeah, I think in general, I just want to make a final point. This is a very pertinent question, okay? And there is this problem of trying to synthesize it completely automatically, like I mentioned. Theoretically, it is undecidable. Therefore, which means that you cannot expect complete automated solution, which is not so bad when you look at it in a different way. So there is more scope for different techniques, maybe learning techniques, using machine learning, other things. There are various whole branch of research, okay, that is done to see how this thing can be done. Okay, how to guess better inductive invariance, or how to refine how to make up good abstractions and how to make when you know that you don't that your abstraction is too coarse, how do you fix it? They are challenging questions. I think this is, yeah. So if there are no more questions, and I mean, it's a good point to stop.
Yeah.
Any more questions, Ameya or Diganta?
No, yeah, everything.
Yeah, sure. So we'll meet on Monday usual time, and
Correct. Yes. Yeah.
Okay. Yeah. Thanks.
Yeah.
I'll have to.
Thank you.
Okay, thank you.
I will upload it right away for the benefit of others, and yeah, and some more material about this supplemental thing, really for simplex and so on. Yeah. Okay.
Yeah. I'll also upload the slides and the paper from which.
I think that is important. Yeah, I forgot to mention that. So
yeah, I'll do it by lunch.
Upload the slides. I'll upload your video, the video.
Yeah.
So that they'll be ready for the next.
Certainly.
Yeah.
Certainly. Yeah. Sure.
You can stop sharing. Yeah.